Hello, my name is Manuel Torre. I'm an MSRP intern from the University of Puerto Rico, and today I'll be presenting an article that I have found to have a major impact in the current suturing technologies we have in the medical practice. It's titled Dry Double-Sided Tape for the Adhesion of Wet Tissues and Devices. First, let's think about what we may know from traditional suturing methods. Materials like nylon, silk, and polyester have been used for a long time in the surgical practice. However, suturing techniques rely on how well they can be executed, and we still find error. So what are some things we can do to alleviate these limitations? Is it something like the super adhesives you may find in a hardware store? Well, sort of. These are some of the current methods for open wound sealing. Some of these sealants are even capable of carrying anti-inflammatory drugs, which increase tissue granulation, remodeling, decreasing pain, and avoiding excessive scarring. Other needed drugs could be applied if necessary. However, all of these products lack sealing time efficiency and sealing capabilities, lacking strong bond formation with the substrate surfaces attributed to their inability of the removal of water from substrate surfaces. Binding is dependent on how well a polymer can use intermolecular forces as well as covalent partial bonding to use substrate for sealing. These methods were inspired by some of nature's architects. For example, spider web glues, which remove interfacial water from the contact surfaces in order to form bonds. Therefore, adopting a cross-linking mechanism to remove interfacial water and form adhesion on wet tissue surfaces was designed. Some components that are found in this polymer are polyacrylic acid and PAC-NHS ester, which these are cross-linked to gelatin or chitosan. Negatively charged carboxylic acids in the PAC-NHS ester facilitate quick hydration and swelling of the DST. NHS ester groups grafted on the PAC-NHS also couple covalently with primary amine groups in various tissues within a few minutes, without the need of further pressure. What also is important to remark is that DST exhibits the ability to stretch to more than 16 times the original length, capable of mechanically matching soft tissues. Embryonic fibroblasts were used to study biodegradation and cell viability at 37 degrees Celsius, being a well-established model for cell growth. In vitro studies showed no observable decrease in the cell viability. Additionally, biopolymer had the ability to be degraded by endogenous enzymes like collagenase, lysozyme, NJase, and varying rates. Forcing tests were carried out to determine tissue adherence in open wound models. Durability of the adhesive depended on whether gelatin or chitosan-based DST was used, gelatin for a durability of weeks and chitosan for a durability of months. However, adhesion capabilities may vary in tissue type adhered by the DST. This is why variables like interfacial toughness, shear strength, and tensile strength were measured. Shear strength measuring strength of the material against the type of yield or structural failure when the material breaks. Interfacial toughness, which quantifies the resistance of crack growth along the interface. Tensile strength, which is the force required to pull the material to the point where it breaks. DST demonstrated that it had superior adhesion performance compared to other tissues adhesives as well as better timing for adhesion between 5 seconds and 30 seconds. Shear strength and artificial toughness and tensile strength were compared amongst the products, and DST showed remarkable results. Some takeaways of this article was the durability of seal is dependent on biopolymer-based, either hydrogel, chitosan, and gelatin, or their rearrangement of how are they combined. This method is capable of for drug deposition in wound healing process, and also capable of medical device adhesion. And one important factor was that it was inspired by making nature's mechanisms for adhesion, such as the spider web. Some acknowledgements I would like to make is that the MIT Summer Research Program for letting me have this opportunity of being with them this summer as an intern, Professor Paula Hammond and Ella Days and other members of the Hammond Lab for serving as mentors for me in the summer, and the Zala Lab for writing this article, which showed great advancement in the medical practice.